Welcome back to the Mechanics of Solids lecture series. In this video we're continuing the example we started in the last video, noting that T is equal to T1 equal to T2, and we're trying to find T so that the shear stress in tube section 2 is less than the allowable shear stress. The formula that we need, the relationship between shear stress and torque, is tau equals TR over J. Note that we want to solve for T, so we can invert this and isolate T. T equal to, in this case, tau2 allowable times J2, the polar moment of inertia for that tube section, divided by R2. We're going to solve for torque. Our working units for this problem is going to be kips, inches, and KSI. Okay. Note that we need to solve for the polar moment of inertia, J2 for a tube section equal to pi over 32 times the outer diameter to the fourth minus the inner diameter, which I'll call D2 to the fourth. And we saw in an earlier video that the outer diameter, or the inner diameter, is equal to the outer diameter minus 2 times the thickness. So I'm going to quickly tabulate that. The outer diameter 1.5 inches. The inner diameter D2 equal to D2 minus 2T, which is 1.5 inches minus 2 times 0.125 inches, which computes to 1.25 inches. So I'm going to come back and substitute that in this formula, minus 1.25 inches to the fourth. Okay, so doing the computations for that one, we get that J2 equals 0.257 inches to the fourth. Now I have everything I need. I'll substitute it into this equation up here. T is equal to tau2 allowable, which is 6 KSI, times my J2 value, 0.257 inches to the fourth, divided by the radius, which is going to be half the outer diameter, or 1.5 inches divided by 2. And this computes to 2.06. Let's check out our units. We have a KSI, inches to the fourth in inches, so inches to the fourth and divided by inches divided by square inches all cancel out, and we're left with inches at the top. We're left with total units of kip inches, which is what we expect for a torque. So that's somewhat of a reality check or a logic check for this part of the problem. Okay, let's go to a new page for the second part. We found the torque of 2.06 kip inches. In part B, we are asked to find the rod diameter D1 so that tau1 is less than or equal to tau1 allowable. And we're going to apply the same formula that we did in the previous part, the relationship between shear stress and torque. Tau is equal to TR over J. Now we have a solid section here, and we're trying to find the diameter to limit the stress to a certain value. So I'm going to expand out both R, this side of the equation, R and J, in terms of the diameter, the unknown diameter D1. So I have T carries over, R is equal to D1 over 2, and J for a solid section, not a tube section this time, but a solid section, pi over 32 times D1 to the fourth. This simplifies a little bit. I have the 32 is going to come up top, divided by 2. I have 16T, and then over pi, I have a D1 on top and a D1 to the fourth on the bottom, reduces to D1 cubed on the bottom. Okay, so now I can manipulate this a little bit further to solve for d1. I'll solve for d1 cubed first, equal to 16t over pi times tau 1 allowable. The numbers are 16, the torque that we found before, 2.06 kip inches, divided by pi, the allowable shear stress, 18 ksi in this case, which computes to 0.58. And what are the units? Kip inches divided by ksi. Those per square inch is going to come up to the top. The kips cancel out and we're left with inches cubed, which is what we expect. We take the cube root of that to get the diameter. The cube root of 0.58 inches to the cube, and that gives us about 0.84 inches for the inner diameter. And our logic check for this one is simply that that inner diameter is within the range we expect. It's less than the diameter of the tube, but it's a large enough value that it seems reasonable. And so we conclude.